Hello everyone, in this video we will complete the chapter 11. In our last lesson we did some examples for finding a power series representation of functions. We have a basic formula for this. The power series representation of the function 1 over 1 minus x is equal to the right side of the equality 1 plus x squared and so on. If the absolute value of x is less than 1, it is obtained obtained by the geometric series. And if you remember, we did this proof in our last lesson. This is the handwritten note 4, and we did some example about that. And lastly, we have an example which is a function given ln 1 plus x. So we will find a power series representation for this function using the lecture note. You can see the answer easily. So for this we will benefit from a formula. When we take the derivative of this function or its power series representation, we get a power series representation for its derivative also by taking the derivative of each term of the power series representation of the basic function. Therefore, we should notice that the derivative of logarithm function ln 1 plus x is equal to 1 over 1 plus x. If you remember, when we have a logarithm function ln f x, so its derivative is equal to the division of two functions, such that in the numerator we have the derivative of f x like that, and f of x. Therefore, when we consider ln 1 plus x, ln 1 plus x, ln 1 plus x, its derivative is equal to its ln ln 1 plus x over 1 plus x. The derivative of 1 plus x is equal to 1, and we write the function itself in the denominator. So by using the basic formula, we can find a power series representation for this function 1 over 1 plus x by writing it as 1 over 1 minus x. If you remember, in the denominator we have to have minus x, so to get minus we write plus x as minus x, and we will write minus x for every term of the power series representation written here. Therefore, for every term x squared, x cubed, so we will write minus x. So here we have plus x. If you write minus x for it, we obtain minus x. For x squared, we write minus x squared. Actually this is minus x squared. So since we have even number for the power, it becomes plus x squared. And similarly, for the next term, if you write minus x, since we have odd number for the power, we obtain minus x cubed and so on if the absolute value of x is less than 1. And you know the derivative of ln 1 plus x is equal to 1 over 1 plus x. Therefore ln 1 plus, if we integrate both sides of this equation, we obtain the integral of 1 over 1 plus x is ln 1 plus x, since the derivative of ln 1 plus x is equal to this function, and the integral of the right side can be found by integrating each term of the power series of the right side. Therefore ln 1 plus x will be equal to the integral of 1, which is x, the integral of minus x, which is x squared over 2, and so on. And of course we have integral constant bigger c, and by looking at each term here, we can find a general term of the power series representation of ln 1 plus x. You see first term, third one, fifth one, namely the odd terms, has plus. The other terms, which are even terms, have minus sign. Therefore we write minus 1 to the power n minus 1. If you write 1, we get 0 for the power, which is equal to 1. Therefore we obtain x if you write 1, and similarly you can obtain all terms by writing natural numbers for n here, plus integral constant if the absolute value of x is less than 1. So to determine the value of c, we put x is equal to 0 here, because this is equal to ln 1 plus x. This is the power series representation of this function, and to get rid of c, which is the integral constant, we write 0 to find it in this equation, and we obtain, if you write 0 for x, we get ln 1 for the left side. Therefore you know it is equal to 0, and the right side, the power series becomes 0, because when we write 0 for every x, we obtain 0, so we obtain c is equal to 0, and as a result we obtain the power series representation of the logarithm function ln 1 plus x is in this form. Okay. Similarly, let's find a power series representation for arctangent x, or tangent minus 1x, arctangent x. So we observe that the derivative of arctangent x, you know, is equal to 1 over 1 plus x, because if you remember, the integral of, from calculus 1, the integral of 1 over 1 plus x squared dx is equal to arctangent x, if you remember, plus some constant. So as you can see, this is equal to arctangent x, arctangent x, and we have a power series representation for 1 over 1 plus x squared. In the first example, if you remember, we found a power series representation for 1 over 1 plus x squared here, which is equal to 1 minus x squared plus x to the fourth, and so on. Using this, you can easily find a power series representation for arctangent x, writing the power series representation for 1 over 1 plus x squared, and integrating each term here, we obtain arctangent x is actually equal to arctangent x is equal to the integral of 1, which is x, the integral of minus x squared, x cubed over 3, and so on. Similarly, in order to find the integral constant, we write 0 to get rid of all terms, continuing infinitely many, and we obtain arctangent 0, which is equal to 0. Therefore, arctangent x will be equal to the infinite sum, which is written here. And you can find easily general term by looking a few terms here. You see we have odd numbers for the power of x in each term, and we have the same number in the denominator for each term. Therefore, we write 2n plus 1, and we write the same general representation for the denominator, and you see it is continuously alternating. Therefore, we write minus 1 to the power n. Actually, it is alternating series, since the radius of convergence of the series for 1 over 1 plus x squared is equal to 1. If you remember the theorem, the radius of convergence of this series for arctangent x is also equal to 1. It is valid if the absolute value of x is less than 1. So now we will see very important theorem to define Taylor and Maclaurin series. If f has a power series representation at some number a, that is the function f is equal to the infinite sum written here. Cn are the coefficients depending on the variable of the sum, x minus a to the power n, and this is the interval of convergence. Then its coefficients are given by the formula. Cn is equal to the nth derivative of f at a over n factorial. So we see that if f has a power series expansion at a, then it must be of the following form. So if you want to find the power series representation of a function, you can use this formula, and you can find the coefficients of the terms, which are Cn, by using the formula written here, and so on. So the series in equation 6 is called the Taylor series of the function f at the number a, or about a, or centered at a. For the special case, namely if you write 0 for a, just we will have x to the power n instead of x minus a to the power n. So the Taylor series becomes f nth derivative of f at 0 over n factorial. This is the coefficient formula, x to the power n, and explicitly you can see the terms of this power series representation for f. So this case arises frequently in applied science, so it is given a special name which is called Maclaurin series. If you write 0 for a in the formula of Taylor series, you will obtain a special case which is called Maclaurin series. By the way, how can we find the formula for the coefficient Cn?